So let's move to the next topic, uh, filter designing by frequency transformation method. We have already talked about that when we are dealing with this digital filters. We are basically talking about two frequencies, the analog frequencies and the digital frequency. Okay, so the frequency transformation, it can be implemented in either of the methods. So in the first case, where you apply the analog frequency domain transformation, that means over there you apply the frequency transformation method in the analog domain only, that means in the HS fraction only. Okay, and once you get the new transfer function, then you can apply the other methods like your impulse invariant method or bilinear transform method over there to move to the digital domain. Okay, on the other hand, in the second case, where we say that the frequency transformation is being applied in the digital frequency domain, what we have HZ, and in the HZ we apply the transformation method equations. There are certain equations, so we will be applying those equations, and it will be converted to the another type of the filter. Okay, so usually if you see, in most of the cases, what is happening, we are designing low pass filter. Why? Because previously also I have told that the designing of the low pass filter is quite easier. So since it is easier to design the low pass filter, so in the frequency transformation method we use the low pass filter as the starting filter. Why? As I told you, it is easier to design the low pass filter, right? Now if you look into the frequency response of the low pass filter, we are having this low pass filter. Okay, now if you want to change the frequency response, say you want to increase the band, so it may be say 3 pi by 4, 3 pi by 4 or whatever. Then it may be a smaller region also. So this smaller region also you can shrink the region, you can expand the region, whatever you want to do, you can do. On the other hand, if you want to make it to a band pass filter, that is also possible. So what we need to do, we need to separate this area and we need to separate this area. Okay, so this area it moves over here and the second area it moves over here. So in that way we can have it. Next, what we can do, we can also design it over here. So in the minus pi to pi region, if you see this region and this region, the area remains the same. Okay, it comes over here, it comes over here. Okay, so in this way we can look into the stuff. Okay, similarly we can go for this band stop filter and all these things. So band stop filter, it would look something like this, whereas band pass filter, it would look something like this, right? Now let us look into the analog frequency transformation. So the first one is low pass filter to low pass filter. Okay, so in the low pass filter, so what we are having, see, omega p divided by omega dash p. So the omega p, it is the edge frequency of the available filter. Whatever is your frequency component, that you will be taking, and the edge frequency of the filter to be designed. Okay, so basically the previous one is fc of the original filter, cutoff frequency of the original filter, and the next one is the f dash c, the cutoff frequency of the filter to be designed. So your s, it would be replaced by this omega p by omega dash p multiplied by s. This is as simple as that. Okay, so if I give you say some filter hs equals to something, so you need to replace s with this thing. So you will be given with the frequency, cutoff frequency of omega p, and also the cutoff frequency of the filter to be designed. So you just need to replace that thing. Okay, so you can get a 2 marks question from there. So coming to the low pass filter to high pass filter, omega p multiplied by omega dash p. Again, this is the cutoff frequency, and it is the cutoff frequency of the filter to be designed divided by s. Same method, you will just put the value, replace the value of s with this one, and you will be getting the high pass filter. Then low pass filter to band pass filter. So if you see, we are having s is being transformed to omega p, that means the pass band filter, because if you see in a band pass filter, sorry, this is for the low pass filter, so sorry, so this is for the low pass filter, whatever the filter you have designed, the cutoff frequency fc, okay, multiplied by s square plus omega l plus omega u. Omega l is nothing but, if you see, the low cutoff frequency, omega u is the upper cutoff frequency of the band pass filter, okay, divided by s multiplied by omega u minus omega l. Okay, now coming to the low pass filter to the band stop filter. So over here it is given by s equals to omega p. Again, omega p is the fc of the given filter, s multiplied by omega u minus omega l divided by s square plus omega u omega l. So these equations you need to remember. Okay, so these were about the analog frequency transformation. So after the transformation, if I ask you to convert it into a digital filter, then you will be either applying IIR filter or sorry, impulse invariance method, or you may be applying the bilinear transform method, or you may apply the differential backward differentiation method, which we will be discussing in a few moments of time. Okay, so you can do this. Now next comes the digital frequency transformation. So in the digital frequency transformation, again your LPF will be converted to LPF. So it is given by Z inverse. It will be transformed to Z inverse minus of alpha divided by 1 minus alpha Z inverse. Okay, so now this alpha, it is nothing but sine of omega p minus omega dash p divided by 2 divided by sine of omega p plus omega dash by 2 omega dash p divided by 2. Okay, so you will just put it over here, and whatever the solution will be there, so that fraction you will be putting it in place of the Z inverse. Okay, so that will convert your low pass filter to the low pass filter of the desired frequency. Then low pass filter to high pass filter, Z inverse, it will be transferred to transform to Z inverse plus of alpha divided by 1 plus alpha Z inverse. Herein the alpha is given by cos of omega p plus omega dash p divided by 2 divided by cos of omega p minus omega dash p divided by 2. Okay, in the next case, we have low pass filter to the band pass filter. So first we have to define certain things. Here the certain things are k. It is given by cot of omega u minus omega l divided by 2 multiplied by tan of omega p by 2. Okay. And alpha, it will be given by omega cos of omega u plus omega l divided by 2 divided by omega cos of omega u minus omega l divided by 2. Okay, so using these two, k and alpha, we will be calculating alpha 1 and alpha 2. Okay, so alpha 1 is given by 2 alpha k divided by k plus 1, whereas alpha 2 is given by k minus 1 divided by k plus 1. So using all these fractions, we will now be transform. We will use the transform function, where Z inverse will be transformed to Z to the power minus 2 plus alpha 1 Z inverse plus alpha 1 divided by alpha 2 Z to the power minus 2 minus alpha 1 Z inverse plus 1. Okay. Now low pass filter to band stop filter. In a similar way, we will be calculating this alpha and this k. Okay. In the previous case, we are using cot. Over here, if you see, this is 10, and with subtle, see over here it was cot and 10. Here it is both the things are 10. Okay. So same thing. you will be getting the alpha, you will be getting the k value. Then using the alpha and k value, you will need to calculate alpha 1 and alpha 2, and then in this equation you put the values of alpha 1 and alpha 2 to get the transformation equation. Okay. Now next is filter design by approximation of derivative. So how do you find out the derivative in the digital domain? The digital domain, as you know, in any derivative it is delta y by delta x. Okay. And any digital data, if you see, x is nothing but your time and y is your amplitude. Suppose you will be getting a series of things, so say 0 1 2 3 4 5 6. So then you will be having some amplitude, say for example 5 6 7 8 9 10 11 so on, right? Now dy by dx, what is dy? Next instance minus the previous instance. So uh, it can be determined by two methods. One is, say, for the sake of example I am showing xn minus of x of n minus 1, where you are taking the previous value. Okay, so it is called backward differentiation method. Divided by time, delta x is delta t basically, and delta t is nothing but your time period of the digital signal, okay, which is equal to 1 by fs, right? So xn minus of x of n minus 1. Okay, so here see xn minus of x of n minus 1. Okay, so this is the backward differentiation method, where you are using this xn and its previous instance value. Okay, so when you try to get the derivative, you will have to use 1 yes 6 minus 5 divided by 1 minus 0, that is equal to 1. Okay, so 1 by 1. Similarly over here you will be having 7 minus 6 and divided by 1. So this is the backward differentiation method, and there is another method which is regarded as forward differentiation method, where you will be using the next value. So it would be 5 minus of 6, then 6 minus of 7, like that. So it would be xn minus of x of n plus 1 divided by t. Okay, however if you see, it is using the future values. Okay, it is using the future values for the calculation of the derivative. So for the digital filters, this forward differentiation method, it cannot be used. Okay, it cannot be used, hence you will find the that the filter designing by the approximation of the derivatives, we are using the equation of the backward differentiation method. So dy by dt, t equals to nt is equal to y of nt minus of y of nt minus t divided by t. So this thing, so this is the hs. So if we apply the z transform over here, so our hz, it would be 1 minus of z inverse divided by capital T. So from here it gives s would be transformed to 1 minus of z inverse divided by t. Okay, so if you look into the numerical, convert an analog bandpass filter to a digital filter by backward difference derivative method. So just if you see, this is being transformed into with this equation, s equals to 1 minus z inverse by t. So we are converting it into the digital filter. Okay, so rest of the methods you will be knowing, right? Now coming to the structure realization method, so there are certain methods, six methods basically: direct one, direct form 1, direct form 2, cascade form, parallel form, transverse direct form, and lattice structure form. We will not go into the details of the lattice structure form. We will be concentrating our lecture onto the first 5 forms. If you look into the direct form 1, this is nothing but what we have been doing in the FIR filter. Simplistically, feeling sleepy? No. Okay. Simplistically, you solve the equation and you just draw the structure directly from there. Okay. So if you see some of the components, they are having components like yz, and rest of the components, they are the input components. Okay. So if you see, uh, on the left hand side we will put xz, on the right hand side we will put yz. Okay. So xz components we will figure out, these are the xz components. So in the first case there is no delay, so this is passing through the B0 multiplier and it is going to the adder. Okay. Next one is xz is being delayed and then multiplied with B1. It is getting delayed, then multiplied by B1, and then it is getting added up with the previous component. Say if this is A, this is B, so this is B, it is getting added up with A. Right. Next, what happens? Two times delay. Already one delay has been has happened with Z inverse. Then another delay it is happening the input, and then it is being multiplied with B2. Say this is C. So at this node, what we are getting? A plus B plus C. Right. This is simple. Then what is happening? This addition, it is directly going out to yz. Now from yz we are delaying the yz output, so this is being delayed, multiplied with minus of a1 multiplier, and then it is getting added up with a plus b plus c. So यहाँ पे फिर if you consider this as d, so we are adding up d. Similarly again this is only left with, so again it is A. So if we say it as E plus E. So see all the components whatever we have discussed over here, they have been added up to give us yz. Okay. So just by looking into the what you call equation, we will be able to do it. Okay. So this form of realization, it is called direct form 1 realization. Next we will go to the direct form 2 realization. So herein we know that xz it is equal to yz by xz, right? Now we will be breaking this down. What we are doing, we are telling y of z divided by w of z multiplied by w of z divided by xz. Okay. So this w, since we can cancel it out, so we can break it down into this thing, and we can say that this is some transfer function h1z, and this is another transfer function wz by xz. It is the second transfer function h2z. Okay. So if you look over here, what is happening? What is happening? We have put yz first and h2z at a later stage. Okay. Now under normal circumstances, if you see over here, we have got this thing, right? Now what we need to do? This has been brought over here, and this part it has been brought over here. Okay. If you see z inverse minus a1 minus a2, this one, and this one, if you see, it has gone over here. Okay. Now why we want to do this? We want to do this because if you look into these two values, so what will happen? These two can be clubbed together. Okay. And we can use only two delays to perform all the operation. Okay, that is what it has been done over here. If you see from here to here, by combining these two, we have got this delay, and by combining these two, we have got this delay. So what is happening? Delay, what is that? Basically, delays are delay registers where your values need to be stored. So in the previous case we are having 4 delays, that means 4 values needed to be stored. Now we have reduced that component. So first of all, the mathematical complexity will reduce, and also the burden on the processor will also reduce significantly. Okay, so this is direct form to realization. Now comes the parallel form of realization. Say for example, band reject filter, it is one of the important filter. So in the band reject filter you have to remember that the low pass frequency should be lesser than the high cutoff frequency. Okay, band reject filter, why? It should look something like that. So your cutoff would be something over here. So FL should always be less than f of h. Okay, so in the next stage, suppose you want to design a band pass filter. Here f of h, high pass filter, should be lower than low pass filter. Why? Something like this it will happen. So what is this? This is nothing but the high pass filter. This is the high pass filter, right? And this is the low pass filter. Okay, so whatever you name, so I am just telling you the basic concept. So this low pass filter, its what you call cutoff frequency should be higher than the high pass filter. Okay, now why I have given these two? Because um, if you see H1, we are using 2 subsystems in both the cases. So 2 subsystems means one low pass filter and one high pass filter for designing either the band reject filter or the band pass filter. Now in the first case, if you see in the parallel form, the output of the first system and the output of the second system are being added. Okay, now in the second case, the output of the first system, it is being fed to the input of the second system, and then we are getting the output, final output. Okay, now what does that means? In the parallel form, if you see, suppose I pass the signal through the low pass filter over here. If I pass the signal from the low pass filter, I will be getting this region, no doubt, right? But this high pass domain, it will be completely wiped off. On the other hand, say if I pass the signal through the high pass filter, what will happen? It will pass through now, and low pass component, they will be completely vanished. Okay, but we want both of this region, both say A and B regions, both of this low pass and high pass region. So what we do, we pass the same signal through both H1 and H2, and the output of these two filters are being added up, okay, to get the final output. And this is what we have seen over here. So this A is your low pass filtered component, B is your high pass filtered component, and since we are adding up both these frequency components, they will be present in the final output. Okay, in the band pass filter, what will happen? Suppose you first pass it to the high pass filter, this region you have got, okay, but you are having it up to infinity, frequency up to infinity, you are getting the signal components, right? Then you will be, the same signal should be band limited and you pass it through the low pass filter. Contrarily, if I first pass it through the low pass filter, then this low pass region would be there. Then if I pass it through the high pass filter, this would be there. And if you see the overlap area, this shaded portion is the overlapped area, and we get the thing. So in the cascading, what is happening? It is basically the multiplicative system, whereas parallel form you will be having the additive system. Okay, so suppose you get something, say 1 by, say, z inverse minus a into z inverse minus b. Okay, so it can be implemented either in the parallel form or in the cascade form. If you want to do it in the cascade form, it is easier because you have to convert this, convert the this what do you call, the transfer function into a multiplicative form. Okay, so this is a subsystem, this is another subsystems. So when in between you are having multiplicative terms, then it is regarded as you need to understand that you have to implement the filter using the cascade form, realization form. Okay, on the other hand, if you convert it into, say, I am not writing the whole thing, say h1z, uh, not h1z, yeah, let me use the same thing, z inverse minus a plus 1 by z inverse of minus b. Say if I can convert the equation into this form, the same equation, then it will be implemented through the parallel form realization. Okay, so it is up to you what you want to do. So depending upon the nature of the h1z and h2z and the mathematical operation what is being performed, whether multiplication is being performed or addition is being performed, depending upon that you can either uh, implement the filter through the parallel form or the cascade form realization. Okay, then coming to the transposed direct form. In the transposed direct form, if you see, uh, we have the this what do you call, a signal flow graph or the realized filter over here. Okay, if you see, this is the filter what we will be discussing. So the same thing, if you see, we have implemented it over here with certain modification. This b2 is not there. Okay, but just for the sake of understanding, you look over here. So suppose we are having a realized filter over here, and that should be, if you see, we are having these z inverse terms which are commonly present for both input and the visor. That means for performing the transposed direct form realization, we need to start with the direct form to realized filter. We need to start with the direct form to filter realized filter, and from there we have to proceed. So what is the second thing? First thing, in the first step, if you see, what you need to do, we need to reverse the direction of the signal flow. We need to uh, reverse the direction of the signal flow. So this is the original signal flow which we have drawn it from the previous one. These are the same. Now the first step, what we have done, we have reversed the direction. So see, initially the signal was going over there, we have just inverted the arrows in all the directions. Okay, then interchange the input and the output. Okay, so what we have done, YZ we have taken it over here and XZ we have taken it over here, right? Third point is reverse the roles of the nodes. Okay, it will automatically be done. If you see previously, if you look into this node, what was happening, it was a splitting node. That means a signal was coming, and from this node the signal was being splitted into two. However, if you look over here, now what is happening over here, two signals are coming and we are getting an adder. Okay, so what does this mean? This means the summing points, it becomes the branching point, and the branching points, it becomes the summing point. Okay, so just by applying these 2 to 3 nodes, we get into the or we get the transposed direct form realized. So just by altering the thing, so that in the conventional form, where xz is in our left hand side and yz is on our xz is on our left hand side and yz is on our right hand side, we get the same thing. Okay, so what is the advantage of this one? In the previous case, in the direct form 2 realization, if you see, there is no feedback loop. So this type of filter, it is called feed forward network. Okay, so all the things, they are moving towards the forward sum, but there was no feedback. So by applying this thing, this transposed direct form, by converting the direct form 2 into through the transposed direct form, we have been able to create a feedback loop from the system. And when you are having a feedback system, it becomes it allows you to design the stable filters in a much more efficient way. Okay, so if you look, what we have done, we have converted our direct form to realized filter into the this transposed direct form realized filter. Okay, now coming to the integrators. Yeah, coming to the integrators, the first one is the rectangular integrator. So I hope all of you know what the integrators does. So integrators, they help you to calculate the area under the curve, basically, right? So rectangular integrator, they will be calculating the rectangular area. If you see, we are having this rectangle, you are having this point and this point, and it is just taking a particular rectangular area and it is calculating the stuff. However, if you see, there is a certain area which is not taken into account. Okay, the main advantage of the rectangular integrator is that it is the fastest integrator, but the problem with that is that with this type of filter is that it is having large errors, because as I told you, these shaded areas, this area, it is not taken into account during the calculation of the area under the curve. Okay, so its equation is like this, and if you convert it, you get this: z equals to t multiplied by 1 by z inverse, and it will be having a modulus of z, modulus of h of omega as this one, and phase of z, it will be something like this. Now if you look into the pole zero plot, it is basically, it looks like a low pass filter, and its realization is something like that. Okay, then coming to the trapezoidal integration. Again, in the trapezoidal integration, what you have the rectangular area and you have a triangular area. Okay, the equation of the trapezoidal integrator, it is this one. Then you can convert it into the z domain, and again if you look over here, you will be getting something like this. Okay, and then its realization over here. So again over here, if you see, it is basically a low pass filter. Okay, it is a low pass filter. So you can remember the thing in this way. HD means high definition. So high pass filter is a differentiator. If you remember this, then you can remember that low pass filter, it is an integrator. Just for remembering, because many students they get confused. So this is the easiest way to remember that low pass filter, it is an integrator, and the high pass filter, it is a differentiator. Now you would say एक साथ कैसे हो सकता है, right? Now the thing is that low pass filter, it is an integrator in the role of region. That means when we talk about the low pass filter, it is something like this. So this is the role of area. So after the cutoff region FL, whatever is your straight line, in that region your low pass filter, it will act as an integrator. Similarly, when you talk about the differentiator, below the cutoff region where we are having this role of area, during that region your high pass filter, it will be acting as a differentiator. Okay, okay, coming back to our lecture. So we have this rectangular integration. Its equation is given over here. We have the trapezoidal integration. Its roles, its equations, and all these things are given over here. Then we have Simpson's rule integration, which employs a polynomial integration method. Its equation and the transfer function, it has been given over here, and its pole zero plot, looks something like this. And what is the main advantage? The main advantage over here is that it covers all the area. It covers all the area over here for the calculation of the area under the curve. But it is the most computation hungry method for the calculation of the area under the curve or the integration or doing the integration. Okay, then uh, coming to the last topic of this chapter. So design methods for two pole filters. Okay, so till now we have discussed many things, many like impulse invariant method. We have talked about the what do you call bilinear transform method. We have talked about backward differentiation method. Okay, for the implementation of the filters. Um, but this designing of the filters by the two pole filter, designing of the IIR filter basically. So it is the most simplest thing how you can design the filter. Okay, those are there because those are under the regular curriculum. But if you want to practically do something, usually a two pole filter and all these things, that would be sufficient uh, to produce a filter which can be useful for your purpose. Okay, and using this method you can design any of the filters over here. Any of the filters, whether it is a low pass filter, whether it is a band pass filter, whether it is a high pass filter, whether it is a band reject filter, doesn't matter. Okay, so to start with, um, we have to define the transfer function. We know it is a two pole filter, so it can have two zeros and two a. So we start with hz equals to 1 plus a1 z inverse plus a2 z to the power minus 2 divided by 1 minus b1 z inverse plus b2 z to the power minus 2. So where the locations of the zeros would be there, the locations of the zeros would be there at minus a plus minus under root of a1 square plus 4 of a2 divided by 2. Pole locations b1 plus minus under root of b1 square minus 4 of b2 divided by 2. As simple as that. You can remember it. It is the generalized function. Again, these are generalized thing. Now B1, it is given by 2r cos theta and B2 equals to r square. Okay. And what is theta? Theta is the normalized frequency in radians. Okay, not in degrees. So क्योंकि 2 pi आ गया, it should be in radians. Theta equals to 2 pi fc by fs. ये भी हो जाएगा. B1 equals to 2r cos theta and B2 equals to r square and theta equals to 2 pi fc by fs. Okay. So we need to first choose the sampling frequency. Okay. Then we need to choose the critical frequency for high pass filter and the low pass filter. Critical frequency means the cutoff frequency. Okay. Then for band pass filter and band reject filter, we need to choose the resonant frequency. Now, how do we do that? There are several methods, but the simplest method is that in both the cases, in band pass filter, we have seen there are two cutoff frequencies, f1 and f2. So it is better to convert it in. We use the f1 plus f2 divided by 2, and we will take the central frequency as the resonant frequency. Similarly, for the band reject filter, we will be having something like this. So we will take same f1 f2 over here also. So we will be having f1 plus f2 divided by 2. Okay. So we will be getting the resonant frequency. Now R, that you have to. Now once you come over here, so we need to select the distance R. Now while while discussing about the designing of the filters through poles and zeros, we have seen what role R plays. So that you have to see what would be the gain, because R would define the gain of your system. Okay. So R equals to, you can vary the value of R equals to 0 to 1. Okay. So R is given by R equals to e to the power minus alpha t. So alpha may vary from 0 to infinity. So depending upon what you want to do, you start with, it would be best that you start with 0.5, and depending upon your need, you either increase or decrease it. Okay. Then choose the value of A1 and A2. So for a low pass filter, A1 and A2, these are fixed. This A1 and A2, these are always fixed. Okay. So for low pass filter, 2 and 1, band pass filter 0 and minus 1, high pass filter minus 2 and 1, and band reject filter 2 of cos theta 1. Okay. So यहाँ पे ये देख लो, it is easier to remember. A2 1 minus 1 1 1. Okay. बैंड पास में -1 है, एंड बाकी में 2 -2. लो पास फिल्टर इज 2, हाई पास फिल्टर इज -2, बैंड पास फिल्टर 0, and band reject filter 2 cos theta. And this is the very simple direct form 1 realization method to realize the filter. So you can see we can design a two pole this a digital filter, IIR filter, digital IIR filter, quite easily by this method. This method you will not get in many of the books, but it is, if you are working in a lab and you want to design something, this is one of the simplistic way to design your filters. Okay. So with this we will stop today. If you have any questions, we can discuss.